welcome back everyone. First day after the first exam. Hopefully it went well for everybody. I've started to look at them. I'm not done grading them by any means yet. It'll take a little bit, but not hopefully too long. Preliminary glance at it looks pretty good, so I wouldn't stress too much about it. We'll see results pretty soon. But yeah, let's get back into it. So last time we were talking a little bit about eigenvalues. The whole idea of eigenvalues, which normally are presented in kind of an unmotivated way, at least in a first linear algebra class, is to find one-dimensional invariant subspaces. If you find a one-dimensional invariant subspace for an operator, then what you're saying is that you send vectors in that subspace to other vectors in that subspace. That is, you send a vector to some stretching of itself. This stretching factor is the eigenvalue. Basically, it says that, hey, if you can find a one-dimensional invariant subspace for an operator, then on that subspace, the operator acts like the simplest possible linear map, which is just multiplication. So our hope, our ultimate goal, is to develop some kind of a spectral theory, as people call it. That is, we're trying to break down an operator into simple little chunks. That is, we take the vector space, and hopefully, with luck, we can break it down into one-dimensional or near one-dimensional. For sometimes we won't be able to quite do that, but we can get close into small, low-dimensional chunks that are invariant under the operator. And then on those small chunks, the operator is much easier to understand. If they're one-dimensional, then it's super simple to understand. It's just multiplication. This lets us understand the operators on a vector space in terms of something much simpler, and that will be what we'll build to. So we found out that, for example, lists of eigenvectors corresponding to distinct eigenvalues are linearly independent. This was a good step in that direction. Now we have to ask ourselves the next question, which is, when do we even have eigenvalues? So here's the first one, and this one actually is, I think, a very fun and relatively simple proof. So the first one says, hey, every operator on a finite dimensional non-zero complex vector space has an eigenvalue. Okay, so let's show this. What we're starting with is V. Suppose V is a finite dimensional vector space over C, and T is an operator on V. That is a linear map from V to itself. Let the dimension of V be n, which necessarily, since we're saying it's finite dimensional, is less than infinity. Okay, cool. So it's actually like a regular old finite number. All right. Choose any non-zero V in V. Okay. Then the list. Okay, here's the trick. Here's the cool trick. This is what we'll do. The list V, TV, T squared V, all the way up to T to the N V is linearly dependent. Okay, now that I've written it out, let's talk about this trick. Okay, so the idea of it is that we've said, look, we have a finite dimensional vector space. It's got some number n, that is its dimension. Okay, let's just take any non-zero vector, plug it into T, and then keep plugging that result into T more times. If we do this all the way up to the nth power of T, then we've got a list of length n plus 1, which is greater than n. That is, the dimension is the length of any basis. A basis is a linearly independent spanning set. So this says that n is an upper bound on how long a linearly independent list can be in the vector space. That is, if we take something longer, it's got to be linearly dependent. It can't be it has to be linearly dependent. It can't be independent. I almost got tongue-tied right there. So we've got a linearly dependent list. This says there exists coefficients a1 through an plus 1 in the field, which in this case is C, such that not all are 0, and, or even write this as, here, let me even be slightly better than writing it as an plus 1. It'll look actually a little bit cleaner if I write it this way. Instead of going from a1 up to an plus 1, let me go from a0, a1, all the way up to an. So I can put the powers next to the coefficients. Okay, so such that 0 is equal to a0 v plus a1 tv plus a2 t squared v plus dot 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 all the way down to an t to the n v. Okay, so that is just for saying, hey, it's a linearly dependent list. So we can take a linearly combination of the vectors in that, or we can take a linear combination of the vectors in that list and get out 0. Moreover, we can do so in such a way that not all of the coefficients in this combination are 0. Okay. Now, this gives at least one polynomial p of z, which we'll take to be a0 plus a1z plus a2z squared plus dot 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 all the way down to an z to the n, such that p of t v is equal to 0. Okay, cool. Do you believe that? Yeah, because that's just the definition of a polynomial evaluated at t, a polynomial of an operator. Okay, so let us suppose that this polynomial p is chosen. What I should say, let's not call it p. Let's call it something else. Let's call it let's call it q. How about maybe I don't want to call it p. Maybe what we should do, just to make things a little bit easier. So here's what I'm going to do. Okay, so this gives at least one polynomial. Ex example. This one would certainly work, such that pt of v is 0. Okay, suppose that this polynomial is chosen to be of minimal degree. Okay, so the idea here is that we want to choose this one so that the degree of the polynomial is as small as possible. That is, if there are many different choices of the a's that let us do this, let's choose the choice where all of the coefficients on big powers of t are 0. That is, maybe you have a chance you could do it with like an equal to 1 and other things equal to other stuff. Or there's some other combination where you could do it where an is 0. Choose the one where an is 0. So if there are multiple options, let's suppose that we took the one that is of minimal degree. So this is not necessarily a unique polynomial. You could maybe take a scalar multiple of it, for example, and it would be fine. Okay, so we could take it of minimal degree. All right. So by the fundamental theorem of algebra, there exists a polynomial q over c and a value lambda in C such that, so here's the idea of it. Fundamental theorem of algebra says that a polynomial over the complex numbers has a root in the complex numbers. All right, this is slightly different from over the reals. For example, you could take the polynomial x squared plus 1. This has no roots that are real numbers. But if you go to the complex numbers, then every polynomial has a root. Okay, and so what this says is that you can write p of z as z minus lambda q of z with, well, I guess I should say with q of z non-zero, but that's, I guess, relatively straightforwardly implied by p being non-zero. Okay, so let's think about this then. So pt of v is 0, which means that, now let's write it out, t minus lambda I q t of v is also 0. Okay. Since q has degree 1 less than p, okay, since q has degree, I shouldn't say 1 less, I should just say less than p, just to be clear, because maybe this is a multiple root. So since this has degree less than p, we know qt of v is not equal to 0, since we supposed, and I will just put like a little blank right here and then point back up to the thing we supposed, just for convenience. So we supposed that this is of minimal degree. Okay, so we suppose that it's of minimal degree. Okay, so qt of v is not equal to 0. That is, we said, hey, there's at least one polynomial. We have it right here for some combination of the a's. Let's say if there's multiple combinations, we chose the one that gives us something of the smallest degree. Okay, cool. Now we've got a polynomial that's of lower degree. Correspondingly, when you plug in t and you apply it to v, you can't get 0 out since it's of smaller degree than the thing that we said was the smallest degree, such that if you plug in t and apply it to v, you get 0. So this one can't be 0. Okay, it would contradict minimality. Hence, lambda is an eigenvalue of t, and qtv is a corresponding eigenvector. Oh, whoa, super cool. So all we have to do is look at this right here. This says that qtv is in the null space of t minus lambda I. This thing is not the 0 vector, so it has a non-trivial null space. That means that lambda is an eigenvalue. Whoa, cool. We just showed it. Take a operator on a finite dimensional non-zero complex vector space, you get an eigenvalue. Super nice. Okay, so operators, at least on complex vector spaces, have eigenvalues. One of the things we did here was a pretty useful trick. That is, this part where we got the polynomial of smallest degree such that pt applied to v is 0. What if we could do this so if we apply it to, say, any old vector, you get 0? Let's think about this a little bit more up next. Okay, so in the last proof, we used this little trick where we took powers of t and applied it to something, and we got out 0. Now, we could ask the same question of, hey, can I take a polynomial that, instead of just picking some specific v, is 0 for all of the v's when I plug t into it? That is there a polynomial so that if I plug t into it, I get back the 0 operator? Well, yes. Let's prove it. here's the idea. We'll need one little quick definition. So a monic polynomial, it's just a polynomial whose highest degree coefficient is 1. Let's do an example really quick just to make this clear. It's not a terrible concept or anything like that. So p of z, let's take this to be like 9 or 4 z plus 9z squared, how about, is not monic. However, q of z, which maybe let's do it like a 5z plus 11z squared plus z to the 7th, is monic. That is, pick the z with the highest power. Does it have a 1 next to it? If the answer is no, it's not monic. If the answer is yes, it is monic. Bada boom. Monic just means the coefficient on the highest power of z is 1. All right. We'll use this to define something called the minimal polynomial of an operator. And I'm going to do a proof that is totally different than what's in your book. This is, I think, it's a proof of my own creation, and I think it is much simpler. So if v is finite dimensional and t is an operator on v, then there's a unique monic polynomial p over the field of smallest degree such that p of t is equal to 0. Furthermore, its degree is less than or equal to the dimension of v. All right, that's the claim. Now, let's do it. Proof. Okay. I'm going to start off with our assumptions. Suppose dim v is less than infinity. And in fact, let me just say it's equal to n less than infinity. And t is in LV. Okay. Let's write poly t for the subset of polynomial operators on t of t. So polynomials applied to t. Ooh, my tablet is freaking out there. Let's see. Okay. P of t such that p is in the polynomials over the field. Okay. Now, since 0 is in poly t, i.e. 0, why is my tablet going crazy? There we go. It's the 0 polynomial applied to t. And here's the nice one. Q of t plus p of t is equal to q plus p of t, and lambda q of t is equal to lambda q of t. Poly t is a subspace of LV. Since dim v is finite, the dimension of LV is finite, and we can see that dim poly t is finite as well. So I'll even write equals, say, like, let's call it m less than infinity as well. Okay, cool. So this is finite dimensional. Hence, notice now, since this is an m-dimensional space, the list, I'll write it like this, I, which is just t to the 0, I'll note that out. Okay, t to the 0, so it's like the constant polynomial that is the multiplicative identity of the field, that applied to t squared all the way up to t to the m is linearly dependent, since it is of length m plus 1. Therefore, there exists a0 all the way up through am in the field such that a0 I plus a1t plus dot 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 all the way down to a m t to the m is equal to 0. Suppose we have chosen m, or I should say we've chosen m. So, suppose now, I'll say even like this. Suppose that k less than or equal to m is the largest value such that ak is not equal to 0, i.e. ai equals 0 for I greater than k. That is, this linear combination of these guys, not all 0. I should say that here, sorry. So this linear combination of these guys, which are not all 0, is equal to 0. So there's some biggest one that's not equal to 0. That is, there's one next to the biggest power of t that's not equal to 0. It doesn't necessarily have to be next to m. This one could be 0, but as you go from left to right, you're going to bigger powers of t. And since they're all not 0, there must be a last one that is non-zero. It could be the case that this one is the last one. A to the m is non-zero. But if it's not, then there's some one before it that is. Okay. Then the polynomial 1 over ak times a0 plus a1z plus dot 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 all the way down to am z to the m. And really, if we're assuming that everything bigger than that ak is 0, I could really just write this as ak z to the k. Let's call this, say, p of z is monic and satisfies p of t equals, well, it's 1 over ak times a0 I plus a1t plus dot 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 all the way up to a k t to the k. But since we're assuming that all of the ai's for I greater than k are equal to 0, I might as well just write them anyway, plus 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 all the way down to a to the m, t to the m. This is just 1 over ak applied to the 0 operator, so it's the 0 operator. Hey, the 0 operator is in there, or is equal to p of t. Oh. So, such a polynomial exists. Hence, we can choose one of lowest degree. Oh, okay, very cool. Now, to show uniqueness, suppose P and Q are monic polys of minimal degree such that P of t equals Q of t equals 0. Agree with that? Okay. Now, P minus Q of t equals 0 as well. So take the difference of these two polynomials and notice that p minus q not equal to 0 implies that, okay, so here's the idea. So, or maybe I should write it this way for slightly more clarity. So here's the idea, is we'll say that if p minus q is not equal to 0, then we have a poly of lower degree. Okay. We have a polynomial of lower degree since the coefficient on the highest degree. This takes a long time to write, sorry. Highest degree term of both p and q is 1. So we have something of lower degree. So take p minus q. Well, both of them have a coefficient of 1 on their term of highest degree, which is the same degree, you know, and so you get rid of that one. So we get something of lower degree, which can be made monic by dividing by the coefficient of the highest power of z in it. This would then contradict minimality. So p is equal to q. That is, p minus q is equal to 0. Okay, so we've got a polynomial of minimal degree that is monic such that p of t is equal to 0. Not too bad. All right. Okay, so this piece right here is not proven yet. So we know there's a unique monic polynomial of smallest degree such that p of t is 0. Let's do a definition quick. This unique monic polynomial of smallest degree such that p of t is equal to 0. So the unique monic polynomial of smallest degree such that p of t is equal to 0. We just showed that that exists for any operator t on a finite dimensional vector space. We'll call this guy the minimal polynomial of t. It is a unique polynomial associated to t, and it is of minimal degree, so we'll call it the minimal polynomial of t. Okay, cool. So here's what we'll prove. The first thing we'll prove is we'll prove that for t, an operator on a finite dimensional vector space, the zeros of the minimal polynomial of t are the eigenvalues of t. Okay. As a consequence of the fundamental theorem of algebra, we'll then be able to say is that if V is a complex vector space, then the minimal polynomial of t has this form. That is, you can factor it all the way out into a list of eigenvalues of t, possibly with repetitions, or into a product of linear terms whose zeros are the eigenvalues of t, potentially with some of them repeated more than once. Okay, let's do it. So notice the observation that will help us is this second one. So basically the first one even. Basically the idea is that last time we showed that an operator has at most the dimension of v eigenvalues. So if we show that the zeros of the minimal polynomial are the eigenvalues of t, then it will tell us, since we have, well, at least in the case where you can factor a polynomial all the way out, we have as many eigenvalues as the degree of the polynomial. We can certainly not have more zeros than the degree of the polynomial. And so if the zeros are eigenvalues, and the largest number of eigenvalues we can have is the dimension of the space, a fact we proved at the end of last class, then this will say that the largest number of zeros we can have is the dimension of v, meaning that the largest the degree can be is the dimension of v. Okay, So let's roll through it. The zeros of the minimal polynomial are the eigenvalues of t. Let p be the minimal polynomial of t in LV. Okay. Now, suppose lambda is a zero of p. Then, by the fundamental theorem of algebra, we get the following. P of z is equal to z minus lambda q of z, where q is monic. Okay. Where q is monic and of degree less than p. Hence, think about this real quick. Since p of t is 0, what we get is that t minus lambda times the identity, q of t, is 0. Okay. And because q is of lower degree than p, what we get is that q of t is not the zero map. Oh, okay. Nice. Hence, applying any v in v such that q of t, v, is not the zero vector, which is possible since it's not the zero map, we get that qt v is in the null space of t minus lambda I, and lambda is an eigenvalue of t. Oh, okay, cool. Nice. Now what about in the other kind of direction there? So now suppose lambda is an eigenvalue of t. Okay. Then there exists some non-zero v in v such that tv is equal to lambda v. Accordingly, t to the k of v, well, that's just t applied a bunch of times to v. Well, this is t to the k minus 1 of lambda v, which is equal to dot, 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 all the way down to lambda to the k of v. Oh, okay. Hence, pt of v is p lambda of v. Oh, okay. Since p is the minimal polynomial of t, p of t equals 0, so p lambda v equals 0, and since this is a non-zero vector scaled by some scalar that is 0, p of lambda equals 0 since v is not equal to 0. Thus, lambda is a 0 of p. Very cool. Okay, so we got part A. Now, On a complex vector space, we get that these are all the zeros of the minimum polynomial are eigenvalues of t. Part B just says that on a complex vector space, I can factor the minimal polynomial out. For part B, just use part A and the fundamental theorem of algebra to factor P. Nice. Okay, sweet. So we've got it down. We know that the zeros of the minimal polynomial of t are eigenvalues of t. We know that the minimal polynomial exists. And we know that over a complex vector space, you can factor it all the way down. And basically, it's entirely determined by the eigenvalues of t. Super cool. There's one missing piece that we still haven't touched on yet, this part here that wasn't proven. We'll talk about that one next time, along with the rest of this section. See you later.